This video demonstrates how to interface LCD with STM32 microcontroller. By pressing this push button, this circuit creates a sound, and the text scrolls off the screen from the left side, then scrolls onto the screen from the right side. Then it moves in a back and forth ping-pong motion before settling. We would also review how to configure the CubeMX file for this project and how to write a library for the 16x2 LCD to interface with the microcontroller, including a header file and a .c file. In our .c file, we are going to see how to write our functions so we can use them in our main file. And finally, we would review our main file and see how we put these functions together to configure a simple project for the LCD. We would also take a look at the circuitry of the simple project, how to connect LCD to the microcontroller, how to connect buzzer to the microcontroller, and creating a safe circuit for the buzzer. Well, let's dive in. Let's launch Cube IDE. Navigate to STM32 new project. We wait until it finishes its progress. I'm going to select STM32F103C8T6. This is my microcontroller and I've already marked it. And you can see its features if interested. I'm going to call this project LCD 16x2. And I choose my desired location somewhere in my laptop. You choose your own location. And here you can select the firmware package that is installed on your computer, and you can also select the location of your repository. First of all, navigate to System Core, RCC, and select Crystal Ceramic Resonator for HSE. This is in case we want to use external crystal oscillator. Of course, we can use internal oscillator as well. Then navigate to System and select Serial Wire. This is because I'm going to program this microcontroller using ST-Link. And select pins PA1 through PA7 as GPIO output. These are the pins that are going to be connected to LCD. And I'm going to select labels for them and call them with the same name of the LCD pins that they are going to be connected to. RS, RW, and etc. And these pins are available on our 16x2 character LCD. Pins PA4 through PA7 are going to be called D4 through D7 because they are going to be connected to data pins of LCD. And there is one important note that we must pay attention to, that we are using D4 through D7, 4 ports. Generally, LCD can be configured in 3 ways: 4-bit mode, 8-bit mode, and I2C. 4 and 8-bit mode are similar, but in 4-bit mode we can use less wires. In this video, we are going to configure LCD in 4-bit mode. The LCD pins have been set up. Now let's proceed to configure the pins for the push button and buzzer. I select PB12 as external interrupt. I pull it down and call it push button. Don't forget to navigate to NVIC and enable the external interrupt. And I select PB15 for the buzzer. I call it buzzer as well. Let's configure timer 1 for 1 microsecond. We're going to need it for LCD interface. Navigate to timer 1 and set the clock source to internal clock. As you can see, by default, all the frequencies have been set to 8 MHz, including timer 1 clock as well. So let's go back to configuration. I set the pre-scaler to 8-1. So now timer 1 clock is set to 1 MHz. In time domain, it is 1 microsecond. And we are almost done in project manager, including name and location. By pressing Ctrl S, you save the CubeMX file and generate the code. Now we are going to add a new header file to core include and call it lcd16by2.h. And to source files, we're going to add a new source file, and we're going to call it lcd16by2.c. In fact, we are adding our library to the project. We can exit the CubeMX file, and in our main file, we are going to include the header file of our library. So we include lcd16by2.h file in our main.c file. And we build it so our project files are matched together. Nice. And in timer 1 initialization, in the init2, we're going to write HAL team base start. In this way, we are starting timer 1 and enabling timer 1. This line of code does what we want to do and starts timer 1. Great. Now, in our header file for the LCD library, we need to include main.h file. By including a main.h file, we can access to HAL library and the labels we defined in our CubeMX file. We have access to them and we can use them in our library. Now we are going to declare a function, and by the help of this we're going to create delays in microseconds, and we need this function in our library. And the purpose of this function is creating delay in microsecond. In our .c file, we need to include the header file so we can access to function declarations. Great. And we write comment to indicate that we are going to declare a function in this section that creates delay in microseconds. Before that, we need to be able to access to timer 1, so we define it as an extern because it is defined in our main file. In this manner we can access it. Great. You can also ignore misspellings if interested. Copy declaration of the function and paste it here, and we can define the function body here. To do that, we need to write two underlines, hal underline team set counter. The first argument is timer 1 and second argument is the counter number and value that you are going to set the counter to, which is 0 initially. We have a warning here and it says implicit declaration of function. We can ignore it for now and return to it later after we complete function definition. And while hal team get counter is smaller than microsecond, the first argument is of course timer 1, and we need to do nothing in the while loop. The warning that we encountered is because of a syntax mistake that I made. As you can see, to use these functions to set counter value and get the counter value, we need to write double underlines and single underline between each word. Double underlines at the beginning of the function and single underline between words. I made a mistake, and here between hal and team I wrote two underlines, which resulted in an error, and we need to modify and edit it. So let's edit it. Nice. So this function creates a delay in microsecond for us, and we can use it in our library. Great. As you can see, 0 errors, 0 warnings. Now we are going to declare the next functions. The next function that we are going to declare is lcd send command or send cmd. The purpose of this function is to send the commands that we tell it. It has one argument called command, and it sends this command to the lcd. So copy function declaration, write comment in order to indicate that we are writing a function in this section that sends command to lcd, paste it, and define the function body here. The very first thing that we need to do is to set the RS pin of the LCD to 0 for commands. And this is set in the datasheet of the LCD, which is provided in our GitHub repository. and the link is available below in the description. To that For sending command to LCD, you need to set the RS pin to 0. Also, we need to set the RS pin to 0, RW pin to 0, to say that we want to write something on the LCD, which is most of the time the case we want to do. We usually want to write something on the LCD. So we set RW to 1. You see the labels that we wrote here helps us so much, and we can use them and set or reset GPIO pins. Next, we want to send higher nibbles to the LCD. As long as we are enabling the LCD in 4-bit mode, we can send 4 bits of data at each time, not 8 bits simultaneously and at once. So first we send higher nibble and then the lower nibble. To do that, define a variable called higher nibble and initialize it with CMD, but shift CMD 4 bits to the right because we want to access the higher nibble. Then we're going to send this higher nibble to the LCD. To do that, we use a HAL GPIO write pin function as well. Before that, let me sort my writings so they look better. HAL GPIO write pin. First, we send data to D7, then define D7 pin, and we are going to send higher nibble to it, whatever it is, but make sure to shift it 3 bits to the right and end it with number 1, so we have access to just 1 bit and the most significant bit of the nibble. Great. Then we are going to do the same thing for D6, D5, and D4 to complete our 4 bits. So we copy paste it. We just need to modify 7 and change them to 6 and shift the nibble 2 bits to the right instead of 3. We do the same thing for D5 and shift it 1 bit to the right. And for D4 we don't need to shift it anymore because we just want to access to the less significant bit. And as you can see, 0 errors, 0 warnings. Brilliant. Next, we have to toggle enable pin so the data is captured by the LCD. To do that, we initially set enable pin, then we have a really short delay, something around 50 microseconds. That's why we created microsecond delay function, because if each time that we send a command to LCD it would wait something around milliseconds, then the LCD would be too slow. And finally, again, we reset the enable pin to 0 so it is ready to get next commands or data. Reset it. Nice. After sending higher nibbles, we need to send lower nibble. To do that, define a variable called lower nibble and initialize it with command and the argument of the function that we're writing. But we don't need to shift it anymore because we want to access lower nibble. And here's a warning, and it says unused variable lower nibble. It's absolutely okay because we're going to write the rest of the code and we can ignore it. And this warning will be fixed in no time. And we're going to send the lower nibble to LCD. It is almost the same as what we've just done, so I copy this piece of code and paste it here, and I just need to change higher nibble to lower nibble. Great. This is the key difference between them. And now I need to toggle enable pin again so the lower nibble is captured by the LCD. And at the end, let's write another delay here. 100 microseconds is a safer option, so let's modify it and write a delay at the end of this piece of code. 2. Nice. Now it works just fine, and this is okay. Our function is ready. Let's build it. Great. 0 errors, 0 warnings. Now let's declare our next function, which is LCD send data. The purpose of this function is sending the characters that we want to see them on the LCD to the LCD. In fact, it sends data and characters to the LCD, not commands. We would see their difference during this tutorial. Copy function declaration. Write comment to indicate that we are defining a function in this section that sends data to LCD, and define the function body here. This is almost the same as what we've done in the previous function. So let me copy the code that we've already written and paste it here. The key difference is that RS pin must be set to 1 for data. It is mentioned in the datasheet, and you can refer to the datasheet if interested. And as you can see, the link is provided below in the description to my GitHub repository. So make sure you set RS pin to 1. And yeah, that's it. The other things are the same. In this manner, LCD understands that it is capturing data instead of commands. The next function that we are going to declare is LCD init. And the purpose of this function is to initialize the LCD in 4-bit mode. Copy function declaration. Write command to indicate that we are defining a function in this section. This makes the readability of your code better. And define the function body here. First of all, we need to give some time to the LCD for the settling time. 15 milliseconds might be a good option. Then in the function set section of the datasheet of the LCD, it is written that in order to initialize LCD in 4-bit mode, you need to send a command, and the command is hexadecimal number 2 or just number 2. And this command initializes the LCD in 4-bit mode. Then give some time to the LCD so it can capture data safely. I know that this delay is in milliseconds and it might be a long time, but it's okay because we are in fact doing this just once in each code. We initialize LCD once in our code, so it's okay. Then we need to send hexadecimal number 28 as command to LCD. So we tell the LCD that we're going to initialize it and use both two lines of our LCD and in 5x8 dot format display. You can use one line or two lines of the LCD. In this case, we are using two lines of our LCD. After each command, give some time to LCD to capture the data safely. And there is another section in the datasheet that tells us how to set the display on and off. In order to turn the LCD on, you need to send a hexadecimal number OC as a command to LCD so the display would turn on. And there's another section in the datasheet called entry mode, and we need to increment the cursor initially to initialize the LCD so it can work. So we're going to send hexadecimal number 086 as command to LCD to increment the cursor. You can see all these commands and how to reach them in the datasheet if interested. And finally, we're going to clear the display so it is ready to show data for us and characters and our texts generally. In order to clear the display, we need to send a number 1 as a command to display. Great. And next, we're going to declare our next function, which is LCD clear. In case if we, in the code, if we want to clear the LCD, it just makes our library richer. To do that, we just need to send number 1 as a command to the LCD. It is just, we're just making functions, a complete set of functions for interfacing with LCD. Hexadecimal number 1, or you could just write 1. It clears the LCD for us. Great. Next, we are going to declare the function LCD send a string. So the purpose of this function is to help us to send strings to our LCD rather than characters one by one. So we can write texts on LCD easier. while we haven't reached null character in the string, this function sends characters one after each other to the LCD by the use of the send data function we've already written. Nice, let's build it. Oops, we've got errors. Let's see what it is. In the send data function, which its argument is data, we are sending a CMD, which is for the previous function. This syntax error is created because of the copy paste. So we need to change this CMD to data, and it would be alright then. Let's build it again. Brilliant. Zero errors, zero warning. Next, we're going to declare another function which is LCD set cursor. It helps us to set the cursor on the desired location so we can start writing from there. It has two arguments, row and column. We have our LCD is 16 by 2 and the number ranges from 0 to 1 and 0 to 15. This is the arguments for the function. Let me sort my code so it looks better. Brilliant. Copy function declaration. Write comment in order to indicate that we are going to define a function in this section. And define the function body here. This block of code that I'm writing is approved by AI. So first define a variable called address, and if row was equal to 0, then the address would be hexadecimal number 80 plus colon. Nice. Else the address would be equal to hexadecimal number CO plus colon. This is for the first row, and set the cursor to the first row and the desired colon, and the else statement is for the second row. This else would somehow say that if row was equal to 1, or in the other words, if we want to write on the second row. And then we need to send this address as a command to LCD to set the cursor on the desired location for us. Build it, great. Zero errors, zero warnings. Next, we are going to declare a function called LCD shift right. This function shifts the entire display to the right. And the function body of this function would be so easy, and we just need to send a single command to the LCD. First, write command in order to indicate that we are defining a function here, and define the function body here. We need to send a hexadecimal number 1C, so it shifts the display to the right. And another function declaration would be LCD shift left. We can shift the entire display to the left as well. Shift LCD to the left, paste the function declaration, and define the function body. Again, we need to send command, and command is the hexadecimal number 18. You could see all these numbers on the datasheet which is provided for you. And as you can see, all the function declarations and function definitions are matched and connected together correctly. Nice. Now we need to write our code in the main file and configure the whole project. To do that, we're going to private function prototype section and declare a function called LCD roll. This rolls the text on the LCD for us. No syntax error, great. Copy the function declaration and go to user code section 4, and we're going to define the function here. Paste. So we can define the function here. First, we write command to show that we are writing the rolling block here. This is the block that rolls the text and makes it rolls out of the screen from left and scrolls onto the screen from the right and settles on its place. Write a for loop that ranges from 0 to 13, and in each iteration shift the LCD to the left with a delay of something around 350 milliseconds. It's a good option. In this phase, still we can see the text, but it is disappearing from the left side. According to the datasheet, if we shift the text 40 times, it is scrolled out of the screen and enters the screen from the other side. So 40 is the magical number that you must remember or check it up in the datasheet. Now we enter the invisible phase. Here we cannot see the text, but it has to be shifted 40 times so we can see it from the other side. For my text, this phase ranges from 40 to 25. It may vary for your text if it is different. And again, we have delay here, but do you think we should use a 350 milliseconds again? Well, if you think so, I should say that it is not correct, because the text is not visible in this phase and we just make the process longer. So we make the delay to 1 millisecond, so as soon as the text scrolls out of the screen from the one side and scrolls onto the screen from the other side. And after that, again we enter the visible phase of the text scroll. Here the text is entering the LCD from the right side. For my text, it ranges from 26 to 40. But when I was writing this code, I made a mistake, and instead of 26, I wrote 25. This number is not important, especially if your text is different from mine, so these numbers will vary. And if you want to find the correct number on your own, you must perform a trial and error method. But if you are copying my code exactly and if you want to see whether it works or not, don't forget to write 26 instead of 25 for the initialization of the I integer. The code that is provided in the description and in my GitHub repository is edited and it works just fine and there are no problems. And don't forget to write smaller or equal to 25 for this phase, and this phase must be 26 as you see as a comment here. So the process must be done until 40 shifts, and we continue shifting it to the left, but this time because the text is visible we set the delay to 350 milliseconds so we can see the text clearly. Nice. Now we are going to write the ping-pong block of code. In this block, the text scrolls to the left and it hits the edge and comes back to the right until it hits the edge on the right side. Then it scrolls to the left and settles on its place. Let's see how to write this code. Write a for loop that ranges from 0 to 2. And shift the display to the left with 350 milliseconds because the text is visible. Then we need to shift the LCD to the right with numbers ranging from 0 to 4. But the text must be shifted to the right instead of left. And finally, for my text, it is enough to shift the text to the left, ranging from 0 to 1. And the text will be settled on its place. Great, 0 errors. Now we need to declare another function which is called buzzer beep. In this function we create sound with the buzzer. Let's define the function body in user code section 4. Always write comments. It helps you in the future when you come back to your code and projects. To create sound by buzzer, it's enough to set it to 1 for some time and then set it to 0 again. To do that, we use half-GPIO write pin function. We set buzzer pin to 1 initially. Then a delay of 250 milliseconds must be good. And we set it to 0 again in the same manner. So we copy it and paste it. Don't forget to change set to reset to turn it off. Great. Now we need to define a flag so we know that the push button is pressed or not. We define a flag variable and call it flag push button and initialize it with 0. So the push button is not pressed yet. Now we need to find the callback routine function for our push button. To find that, go to STM32F106C8T6 then find external interrupt function, then go to the HAL function definition. Here you can find a weak function. Generally, you can override weak functions. So copy this void function, we are going to write our callback routine in the body of this function. So we write it on user code section 4. So here we write our callback routine. We just set the flag to 1, so we know that the push button is pressed. Whenever the push button is pressed, the microcontroller comes to this function and implements the routines. In the routine, we've told it set the flag to 1, so we know that the push button is pressed. In the main function, just before the while loop, we're going to initialize the LCD. Then we set the cursor to 0, 5. I want to write a sly fox in the middle of the first row of my LCD. That's why I'm using these numbers. For your text, it may vary. Then write a sly fox on the LCD. Then set the cursor to 1, 3. I'm going to write electronics in the middle of the second row. Then write electronics on the LCD. Great. Now, when the microcontroller is turned on, it writes SlyFox electronics on the LCD. Great. Let's go to our while loop. Always we check whether the push button is pressed or not. And we understand it via the flag. If the push button was pressed, then we create a beep sound by the use of the buzzer. We roll the text on the screen, and again we create a beep sound by the use of the buzzer. The first beep indicates that the process has begun, and the second beep indicates that the process has finished. And finally, we set the flag to 0. Well, our code is done here. This is the schematic of our circuit. We can refer to if necessary. As you can see, our LCD works with 5 volts. The VEE or VO pin is for adjusting the contrast of the LCD. It is connected to a 10 kilo ohm potentiometer. By rotating this potentiometer and changing its value, you can adjust the contrast of the LCD. RS, RW, and enable pins are connected to microcontroller, as well as data pins ranging from D4 to D7 to microcontroller pins PA through P7. Pin PB12 is connected to a push button, and the other head of the push button is connected to VDD. We're going to connect it to 3.3 volts in order not to hurt the microcontroller instead of 5 volts. Pin PB15 is connected to base of an NPN transistor. I've used 2222A NPN transistor. For limiting the current, I've used a 220 ohm resistor. It might be a better idea to use larger resistors such as 1 kilo ohm. And so when the command comes from the microcontroller and it is set to 1, logic 1 comes here, and then this transistor, which by default is open circuit, is short circuited, and the buzzer circuit is closed and it creates a sound for us. And the buzzer also works with 5 volts. I provide the 5 volts on the top rail of the breadboard. If you ask me how do you want to provide the 5 volts for your project, I would say that ST-Links can provide both 3.3 volts and 5 volts. As you can see, pins 7 and 8 are dedicated to providing 3.3 volts, and pins 9 and 10 of the ST-Link can provide 5 volts for us. I've connected the orange wire to pin number 10 so I can use 5 volts on my breadboard. So the top rail provides 5 volts for us. The bottom rail is going to provide 3.3 volts for us via the Blue Pill board. So I connect a 3.3 volt pin of the Blue Pill to bottom rail, and the GND is also provided from the Blue Pill board. I connect both grounds of 5 volt and 3 volts, together, 5 volts and 3 volts together. Great, now our power supplies are provided. Then I'm going to connect VSS pin of the LCD to GND. Then the VDD pin will be connected to 5 volts. VO pin, which is for adjusting the contrast, is going to be connected to 10 kilo ohm potentiometer. I place it on my breadboard. Great. VO pin is connected to middle pin of the breadboard potentiometer. And the side pins are going to be connected to VDD and GND. Generally, we have to provide a resistor around 1.5 kilo ohm for this VO pin, so it gives us a good contrast. When I bought this LCD module, I was a newbie, so I soldered wires to these modules. Of course, it's a better idea to solder pin headers to the LCD. It would save a lot of your time. RS pin is going to be connected to PA1 of the microcontroller. RW to PA2. Enable to PA3. Then I have to find the wire related to D4. And these are the disadvantages of soldering wires to your module. Always solder pin headers to your modules. So connect D4 to A4, D5 to A5, D6 to A6, then D7 to A7. Great. Now I'm going to use a 220 ohm resistor to connect anode pin of the LCD backlight to 5 volts. I can connect it to 5 volts straightly and don't use extra wires. This is for limiting the current and avoid hurting our modules and microcontroller. And cathode pin will be connected to G and D. It might be a good idea to shift these components to left so the right side of the breadboard is free. Then I'm going to place the buzzer on my breadboard. The longer pin is the positive pin and the shorter pin is the negative pin. The positive pin is going to be connected to 5 volts and the negative pin will be connected to collector of the NPN transistor. Positive pin is straightly connected to 5 volts and I connect the negative pin to collector of the 2222A NPN transistor. Good. Now I'm going to connect the base of the transistor to pin PB15 via a 330 ohm resistor. Of course you could use larger resistors and it may be a better idea. Pin PB15 is dedicated to buzzer. Then I'm going to place push button on my breadboard. One side will be connected to 3.3 volts and the other pin is going to be connected to B12 pin. Great. The emitter pin of the transistor must be grounded. Let me connect the emitter pin to G and D. Make sure that the vicinity of the push button is not crowded. All done. Now it's time to upload the code to our microcontroller and see the result. Now it is uploading on our microcontroller. Great. And this is the final result. You see, by pressing the push button, the text scrolls off the screen from the left side and scrolls onto the screen from the right side, and then moves in a back and forth ping-pong motion and then settles on its place. If you enjoyed watching this video and it was helpful for you, please don't forget to like and subscribe, and stay tuned for more videos. Good luck.